Today is day 23 of this course. The topic today, actually, if you look at the pages in the text, it's not very lengthy. Section 2.9 on linear approximations. I'd like to dive into the content, but spend a lot of time on diagrams that are in the text. You'll see this diagram in your text in section 2.9. Here's what we're attempting to do, and this is kind of one of our first uses of the derivative. We're going to use the tangent line to the curve, and if you look at this diagram right here, we're going to use this line that's labeled capital L. We're going to use it to help approximate what's going on the function itself. Now, sometimes that would be a bad thing to do because the curve obviously separates from the line. But if you'll zero in on, for example, somewhere in here to here, don't you think the line does a pretty good job of approximating the curve? Pretty close to it? And in fact, if we get even closer than that, if we work in this vicinity right in here, it's kind of hard on my diagram to distinguish the difference between the curve and the line that's tangent to the curve. So if we want to approximate what's going on a curve, some function, we can approximate as long as the value is reasonably close to A. So we'll go a little bit to the left of A and a little bit to the right of A, and we can't expect it to work any further than that. But as long as we're reasonably close to A, we can use the tangent line to a curve instead of the curve itself. And I think we would all agree that lines are pretty easy to work with. Everybody agree with that? And sometimes other curves are not. I mean, we could have a curve like 3 to the x, or 3 to the x squared, or the sine of x to the 3x. And I don't think we would choose to work with those curves as opposed to some linear function. So we all feel real comfortable with lines and slopes and point slope and slope intercept and all that stuff. So we want to work with lines to help us approximate some other function. Same diagram. I've got some different writing on it. Now the point that is labeled is a point that's in common to the tangent line and the curve itself. Everybody agreed with that? The point at A, this point, is on the line that's tangent to the curve and the curve itself because it is the point of tangency. So that is an actual point of the function. So I labeled it A, comma, f of A. But it's also on the line. Now, if I want the equation of line L, I want it to go through this point, that point of tangency, and I want it to have what slope? Well, what is the slope? If you listen to my question, it answers itself. What is the slope of the line that's tangent to the curve? It's the slope of the tangent, which is the derivative, right? So the slope of the line is the first derivative at A. Everybody feel comfortable with that? Mm-hmm. So we have a point, A comma f of A, and we have the slope of the line capital L, is the first derivative of the function, whatever that function might be, at A, and then we can generate the equation of the line. So y minus the known y value, well, the known y value is f of A, equals slope, well, the slope is the f prime of A, times x minus the known x value, and the known x value is A. So this is just basically point slope. Point is the point of tangency, slope is the derivative. So it's kind of our first application of derivative. Now I want to solve that for y. So y is f of A plus f prime at A times x minus A. Now that's a y value on the line though, right? Didn't we find the equation of the line? So let me put a little subscript there. That's a y value on the line. Now if we stay reasonably close to A, do you think we could use the y value on the line to approximate the y value on the curve? Yes. Now, out here, can I use the y value on the line to approximate the y value on the curve? Probably not. And I did that on purpose. I went quite a distance from A to show you that the line and the curve separate. But in here somewhere, I can use the y value on the line to approximate the y value on the curve and probably get away with it. So we're going to say the y value on the function can be approximated by this thing we know to be the y value on the line. So the y value on the function, as long as we stay fairly close to our initial point of tangency, we can get away with that. And it is linear approximation. It is an approximation technique. So this is what we want. The y value on the function can be approximated by the f at A plus the f prime at A times the quantity x minus A. So we want to do that somewhere in this general vicinity. We want to be reasonably close to A. I can't tell you what that's going to be because it will vary from one problem to the other. It kind of depends on the curve. This curve kind of flattens out, doesn't it? So if the curve is fairly flat, the line is going to stay closer to the curve for a longer period of time. If the curve is steep, if the curve were to look something like this, really take off, well, it separates from the tangent line a lot quicker the steeper the curve. So it kind of depends on the curve what is close to A. I can't tell you what is close to A. Okay, let's look at an example. Let's start, I want to use their example. It's a pretty good one. And the curve, in fact, looks a lot like this curve. It's a pretty nice one to start with. And we have a pretty good handle on some values for the square root of x because we've used the square root function quite a bit. So our function that we want to approximate is the square root of x. What we want to use is a line that's tangent to that curve at a certain point. And let's pick a value. I've got some values written down here. Let's say we want to find the square root of, what did I write down? 0.95 without a calculator. We want to use the tangent line to the curve to help us approximate this. The square root of 1.03. I think we can do a pretty good job with a line without a calculator to get the square root of 1.03. We'll actually get very, very close to that value, surprisingly close, without punching any buttons on a calculator. And let's see, I chose another value. I want to get away from 1 a little bit further. Everybody agreed that all these values are near 1, right? So our A value is 1. That's the value that we want to stay close to 1. We want the tangent line to be tangent at the x value 1. Well, at the x value 1, the y value is the square root of 1. And that's the point 1, 1. So 1, 1 is the point of tangency. Is that okay? Because it's on this curve. So the curve we're working with looks roughly like that. We're going to draw the tangent line to the curve at the point 1, 1. And then we want to use the equation of that tangent line linear approximation, to help us find what's going on the curve itself. Does everybody understand why I picked the value 1? Because it's close to all the values that we are trying to find. So let's find the equation of that line. This is something that I want to do on the first example I want us to do, but you don't have to do this on every example because we already have a way to approximate it. We can sub in. But I want to show that, in fact, that way we're subbing in is, in fact, the equation of the line that's tangent to the curve. So there's the equation of the line that's tangent to the curve at this point of tangency 1, 1. And how do we find the slope? Derivative. Gosh, we might have to do a little problem off to the side here. So for the slope, we're going to find that by the derivative at this specific x value, which is x equals 1. So I'm going to take this off, bring it back here in a minute because we've got to do a problem off to the side. That is to find the derivative of this function. We need to find for f of x equals square root of x, we need to find the derivative. So let's do that. And then we'll come back to this page. So we don't have any shortcuts yet. If you know a shortcut, you can use it to check what we're about to do. What do we have to do at this point? Definition. That's all we have is the definition of derivative. So the function at x plus h minus the function at x all over h. Now this is a type that you're responsible for doing, so kind of think ahead of me here. Think of what you would do if this were a test question and you were asked to find the derivative. This would be a fair test question. What is this function evaluated at x plus h? Okay, square root of x plus h minus the function at x. I can't handle a whole lot, but I think I can handle that one. All over h as h approaches 0. What's next? Okay, don't say that too loud. Everybody ought to have in your head right now what it is you would do with this problem.
Multiply by conjugate.
Multiply by the conjugate, right? I heard several of you saying that. Did the rest of you have it in your head that you would do that? That's a process you'll need to know coming into this next test. If you've got the difference of these two radicals, you'll have to multiply by the sum of those same two radicals, numerator and denominator. And what I just wrote down in green, although it doesn't look too green up there, what is that? That's another name for 1, right? Something over itself. So we didn't change the problem. We multiplied by 1. That's legal. But we're going to change what we have to deal with as a result. So what happens nicely in the numerator? Okay, you have first thing squared minus second thing squared, right? That's the nice thing about multiplication by a conjugate. A minus b, a plus b, a squared minus b squared. So this is a step that you'll eventually do away with. Now it does make the denominator worse. Square root of x plus h squared, x plus h. Square root of x squared is x. What happens in the top? X is knockout. So we have just h. Again, you may not have to take an extra step for this. That's fine. So you said h over h. As long as h is not 0, that's legal. 1 is the numerator, and as h approaches 0, that little piece right there drops out of the picture, and the denominator is the square root of x plus another square root of x. What is anything added to itself? We've got 2 of those things. So we've already done that. We've already let h approach 0. Everybody convinced that, I've told you before, it doesn't do you any good that I know how to do this. It does you absolutely no good that I know how to do this. What's important is that you know how to do this. So I want you to leave today confident that you can do a problem like this on a test. And I feel pretty confident after having gone through that. Yes? Go ahead. Sorry, Jody.
You know how you canceled out the h?
Mm-hmm.
And you didn't cancel out the x? If there would have been like a xh, the x would have canceled out or went to 0 too.
No.
If it would have been multiplied.
Multiplied down here?
Yeah.
Yeah. If that
But
would have
since
been.
they're added, you don't cross.
Since they're added, it's x plus something that's going to 0, and x
So you
plus
take
something that's going to 0 gets closer and closer to x. But had it been x times h, and h is going to 0, then that whole product would go to 0. Lisa?
I just had a question on the algebra part of it. I understand that, but number 43 on the homework was it was the same type of thing, but just a little bit different. And
Was it,
it was the cubed root, and
Yeah,
the way that the solutions book had it, I didn't understand it, so
okay,
I
all
don't
right,
have to go right
we'll
now.
hang on to that then. We can, and possibly
Okay.
have time for that one today.
Okay.
Everybody, any other issues with this? So there's our derivative, which we need in the problem that we were on. So now we had it. We have it. We had to do a little problem off to the side. So the derivative of square root of x is 1 over 2 square root of x. So I can come in here. What is the, let me put that down here. What's the derivative evaluated at x equals 1?
1/2.
1/2? So there's the derivative at 1, which is the slope of the tangent. I don't know if that looks that way to you, but that doesn't look too bad to me, that line, that green line on my figure has slope 1/2. So this is the equation of the tangent line. Now we found that kind of the old-fashioned way, is that we had a point, the point of tangency, 1, 1, and we found the derivative, which helped us generate the slope of the tangent, and then we plugged in the point and the slope, and we've got this equation. Now let's backtrack, and I wanted to do this since this was the first example. What I pointed out on a previous sheet up here, now this is the y value on the line. We're going to use that to approximate the y value on the function itself. Didn't we say that it was the f of a is 1 in this problem, plus the f prime at a times x minus a. Is that correct? Is that what I wrote down earlier in the class? And isn't that what we have in this problem at this point in time? Now, can you skip the development of the linear equation each time? Yes, you can. But I wanted to at least do it once. You can go directly to this as soon as you identify what a is, and if you already know what the derivative is, I mean, that may be a problem off to the side you have to do, but you can basically start with this step right here. So here's our function. Here's how we're going to approximate our y values. In fact, instead of saying the y value on the function, let me just say that that's f of x. I feel a little more comfortable writing it that way. So we're going to approximate the f of x values, y values on the function. The f of 1, well, the f of 1 is the square root of 1. That was 1. The f prime of 1, we did that a moment ago. That was 1/2. Now that may not seem like a big deal to you, but I want to point out something that is in fact a big deal. Although it's not a super complicated function, square root of x is not a real simplistic function either. But we're going to, instead of using a square root function, we're going to use a simple linear equation in place of the square root function. We're not going to take the square root of anything. So if we want to approximate something that's fairly close to 1, let's say we want the f of, what did I say we wanted, 0.95? Right? We want the square root of 0.95. It should be 1, approximately, 1 plus 1/2, 0.95 minus 1. So we're using that simple linear equation, and we're saying at 0.95, aren't we pretty darn close to 1? Let me go back to my picture here. Do you think if this is 1, that if I'm at 0.95, I'm right next to this point, right? Do you think the line is really, really, really close to the curve at 0.95? I can almost guarantee you it is. This is a pretty flat curve anyway. So at 0.95, the curve and the line are practically the same. What is 0.95 minus 1? And we could do this all in fractions, but we probably have a calculator handy. What's 1 plus, well, let's just do it in fractions, and if we need a decimal, 1/2 of, what's negative 5/100ths? Negative 1/20th, is that right? So 1 minus 1/40th? 39/40ths? Somebody check that out with a calculator. We'll check the result out. If you do this on a calculator, that's approximation too, by the way, isn't it? I mean, your calculator doesn't give you the exact answer. It gives you accurate to 10 or 12 or 15 decimal places. What's a calculator say? Square root of 0.95.
0.975.
9.746. Did somebody say?
Yeah, it was
Yeah, 5. Oh, yeah.
Okay. Now what did we get? What is 39/40ths?
0.975.
0.975.
75. Yeah.
That's pretty good, right? That's a pretty good approximation. And it should be, because the line is extremely close to the curve at only 5/100ths a unit of a unit away from x equals 1. Is that process okay? I'm not going to go into quite that much depth for all the others. We'll just basically sub into what we have. So that's the function, the square root function, evaluated at 0.95. We also want some other values. So our function, our true function, is the square root of x. We're approximating this function with this nice, clean little line. I want the f of, what was my other value? 1.03? Do you think that's close enough to 1 that the tangent line is going to be real, real close to the curve itself? It's even closer, right, than the previous example. Notice there's an x here and an x here. Whatever I put into that x position in the function, I put into this x position in the approximation for the function. And 1.03 minus 1 is 0.03, or what, 3/100ths?
Yep.
So what do we get out of that? 3/200ths?
Yep.
What is 1 plus 3/200ths? We'll multiply that by 5. 1.2 .015. Is that right?
Yeah.
Now, from a calculator, what is the square root of 1.03? 1.01
014.
48.
Mm-hmm.
And for what we've got, which is 1 3/200, using our linear approximation, we did a pretty good job approximating a square root with a simple linear equation. And you say, well, sure, it should. 0.95 was 5/100ths of a unit away from 1. 1.03 was 3/100ths of a unit away from 1. How about if we went as far as, what did I say, 1.21? Suppose we want the square root of 1.21. Now it's easy. Whatever you want a square root of, you just plug it into this linear function. See what you get. So that'd be what, 21 over 100? So it ought to be 1 plus 21 over 200. What is 1 plus 21 over 200? I know that's close, because I know what this answer is. It's 1.1, isn't it?
Yeah, 1.105.
This is 1.0.
105. No, 105.
105.
1 point.
And the actual value from a calculator is what, 1.1?
Yeah.
Because 11 squared is 121, so 1.1 squared ought to be 1.21. So that's pretty good. So, and that's not necessarily, right next to 1. Now, when would we expect this separation to occur? I don't know. Could we find the square root of 2 this way? Probably do that in your head. Look at this equation. What would this tell us that the square root of 2 is? Put in 2 for x. 1.5, right? That's not all that good. Square root of 2 is what? 1.414. So we can see the separation starting to happen now. So we're 1 unit away from 1. So there's a distinct difference between our approximation and the actual answer, square root of 2, which is 1.414. But as long as we're fairly close to 1, this ought to be a pretty good form of approximation. So do you have to do that linear thing each time? No. Whatever your function is, you can approximate the function in this fashion. So there's the linear approximation for whatever function we're dealing with.
Is that the difference between when you plug in 2? Is that like the distance between the tangent line and the point right below it?
Yes. That would be on one of my original pictures. Let me come back to this one. So this is 1, let's say, and we're out here at 2. Then we got 1.5 using the line, and the actual value is down here at 1.414. So we've gone to the place where they've begun to separate. Zach,
What was the name of the equation again? The linear.
say that again.
The name of the equation. Linear
It's
approximation.
a linear approximation, or tangent line approximation, or sometimes called linearization. It's got all those names. Tangent line approximation. That's a P. Or linearization. So any of those, they all refer to this same process. You will come to a process later in calculus, Calc 2, 241, where you'll start with this linear approximation, and then you'll be able to develop what's called a quadratic approximation, and a cubic approximation, and a quartic approximation, and then those approximations are used to develop what are called Taylor and Maclaurin series. But this is step one of that, is to use a tangent line to the curve to approximate. Okay, next example. Here's a function that is fairly simple looking, natural log of x. The problem is we haven't found the derivative of the natural log yet. So the natural log function looks something like this, if you were to sketch it. And we've examined a graph like this, so that's why I wanted to do this as an example. As you move further out to the right, what happens to the slopes of these tangent lines?
Approach 0.
Okay, they gradually approach 0. So would it be a problem for you if I said that if this is the function, we'll derive this eventually, but I want to just tell you this for today. Would that be out of line with what you would think would be the case? Doesn't 1 over x, as you let x get larger and larger and larger, doesn't 1 over x approach 0? Mm-hmm. And in fact, this is true. The derivative of the natural logarithmic function at any point is 1 over the x value. So if I'm at x equals 2, then the slope of this is 1 over 2. If I'm here at x equals 4, the slope is 1 over 4. And that seems reasonable, I hope, that that's the case. So if we want a tangent line, let's say, I don't know, give me a value you want the natural log of. 3.71. How about that? Okay, and we want to use the tangent line to approximate it. What's a value that's reasonably close to, we're not going to be able to do that yet. That's down the road a little bit. Because if we were doing that, wouldn't we need to know the, if we pick a value, here's why I'm going to change my original problem. We're going to need to know the natural log of a value real close to 3.71, which we would say, well, 3, well, do we know the natural log of 3? Do we know the natural log of 4? We don't really know that. So I'm going to pick another value that we can know the natural log of that value that's close. So let's reload and get a new original problem. Let's say that we want 1.46. Now the reason I picked 1.46, somebody tell me why I reloaded to that number.
It's close to 1.
Close to 1, and don't we know the natural log of 1?
Yes.
Somebody saying, yeah, I know we know it, but don't call on me right now. It's 0, isn't it? The natural log of 1 is 0 because that's the power you would raise e to get 1. E to the 0 is 1. So let's do this one instead. So we want the natural log of 1.46. Let's do it right here. So we're going to choose a to be 1. That's a value that's close to 1.46 that we already know what the f of a is. So we want the f of 1.46. It ought to be the function at 1 plus the first derivative at 1 times x minus 1. that okay? So there's a lot of repetition. That's one nice thing in this linear approximation. The f at 1 plus the f prime at 1, and then x minus 1. So the same value goes here, here, and here in that approximation technique. What is the function, the natural logarithmic function at 1?
0.
0. That's why I changed from the original problem. The first derivative at 1, well, what did I say was the first derivative?
Over x.
It's 1 over x. So what is 1 over x at x equals 1? That's 1. So x itself is 1.46. That's a pretty simple linear equation that's going to give us the natural log of something. What do we get? So is the natural log of 1.46 approximately 0.46? Somebody check that one out.
.3784.
0.378? Really?
Were we pretty far off from 1 though?
Let's see. Yeah, okay, yeah, that's good. Let's examine the graph. It's not horrible, but it's not as good as I thought it was going to be. So the curve, so we're using the tangent line here, right? At x equals 1. And then we're coming out here to 1.46. Yeah, there might be enough of a separation to get that kind of an error. What did the calculator say?
.378.
0.378. So from a calculator, 0.378. Didn't do a great job. Okay, maybe the reason is because 1.46 is too far away from 1. A little too much separation there. Had we been out here on the curve, we could probably get away with it because the curve is flatter out here. But in here, the curve is still reasonably steep. So didn't quite do as well as we thought we might. Okay, last example. This is a problem in your book. It's in the list of homework, but it's not going to be a homework problem. It's from page 174 in your text. It says the table lists the amount of U.S. cash per capita in dollars in circulation as of June 30th in the given year. Use a linear approximation to estimate the amount of cash per capita in circulation in the year 2000. So notice it goes up incrementally from 1960 every 10 years up to 1990. But we want to use this information, and we don't have a function at all. So it's very different. That's why I wanted to look at one with just a data set as opposed to the function. We don't have anything to go by to go back and sub into the definition of derivative. We've got to find a derivative some other way. So in 1960, the per capita amount of dollars in circulation, $177. 1970, 265, and so on. So what I've done is I've plotted those points. So there's our data set. So I've got an axis, a t-axis, and a c of t axis. And we're going to try to use this information to see what's going on in the year 2000 using linear approximation. So there's what the graph looks like. And I just plotted the data from the table that was handed to us in the problem. Now, another reason that I selected this problem is this data set looks almost exponential. That's very, very close to what an e to the x or some variation of e to the x looks like. So if we were to kind of connect these, you would have a nice, very, very much of an exponential type progression. So I guess the per capita dollars is growing exponentially. So what we want to do is see what's going on at the year 2000. Now the problem is we don't have a function, we don't have a tangent line at 1990. So we want to approximate the c of t. Let's just do this. We're going to approximate the function by the function at a plus the first derivative at a times x minus a. That's our starting point for this linearization or linear approximation. So the value, as close as we can get to the year 2000 with our information, is 1990, right? So that's going to be our starting point. So the function at 1990 plus the derivative at 1990 times x minus 1990. Well, some of this we know, and some of it we got to go off to the side and figure out. What is the f of 1990?
What is it?
I can't read it.
It was in the table, wasn't it?
1063.
1063? Plus the f prime of 1990. We don't know that. Any ideas on how we could get the slope of the tangent to this curve at 1990? Could we use something else that we're handed to approximate that? Notice the difference now. You start approximating using approximations because you don't have the function. You kind of have to
Secant
use.
lines?
Okay, we could use maybe the slope of what's going on from 1980 to 1990, and you find that and use that as an approximation. We don't have a lot to go with. So we'll go off to the side and approximate this value. And then we'll come back in to this. So let's go off to the side and do a problem. Actually, I think we can probably do it up here. So the f prime at 1990, we're going to approximate that by the f of 1990 minus the f of 1980 all over 1990 minus 1980. Does that seem reasonable? That's all we have. That or we can just guess. I mean, I don't know how reasonable that is. So what's the f of 1990?
1063.
1063. What's the f of 1980? And we've got a, what, 10-year increment here? Somebody punch that into your machine and tell me what we get for an approximation of the slope at 1990 using this 10-year increment.
49.2.
49.2? Let me stop here. You think this is going to be an overestimate or an underestimate?
Under.
Underestimate,
Yeah.
right? Simply because of the shape of the curve and the fact that is the slope between 1980 and 1990, is that going to be the same as the slope at 1990? No, the slope at 1990 is probably going to be more, right?
Yeah.
If this trend continues. So there's a couple of reasons why this is going to be an underestimate. So there's our approximating function. And we want to know what's going on at what particular x value?
2,000.
2,000. So there's our setup. Feel comfortable with that? So we've kind of got a couple of approximating things going on. Not only is the line approximating the curve, we've had to approximate the slope of the tangent to the curve. All right, let's see what we get here. Everybody run that through?
1555.
How much? 1555? And that would be dollars, right? And you know this has a unit too. I probably should put this up here. Isn't this dollars per year? And somebody might say, well, what happened to the years? Because we ended up with dollars. Didn't we take this 49.2, which is dollars per year, and multiply it by what? Years. So we're back to dollars. So the per capita income in circulation in 2000 is approximated to be, and we all agree that it's probably an underestimate, approximated to be 1,555. So we can do it if we have a function. We can use linear approximation even if we just have points on the function, but it's not going to be quite as good if that's the case. Okay, if you'll take a look at these problems, just 4 problems from page 173, 1, 8, 13, and 14. And that will finish us from day 23. Appreciate your attention.